Welcome back to the workshop for another example using the integral test. For this example, we want to determine the convergence or divergence of this series, the sum from 1 to infinity of n over n to the fourth plus 1. And again, what we want to do is we want to recognize that this can be written as a function evaluated at the positive integer values. So the function in this case being x over x to the fourth plus 1, right? So if I evaluate at 1, 2, 3, 4, that gives me the terms of our series. So we want to confirm that f is continuous. And yes, it is. Excellent. We also want to make sure that f is positive, which it is. And then we also need to confirm that the derivative is negative, right? We want it to be decreasing. So if we were to calculate the derivative of this function, we would find it to be 1 minus 3x to the fourth divided by x to the fourth plus 1 squared. Of course, using the quotient rule there. So with this, we get that this is negative, right? This is less than 0 for x greater than or equal to 1, which is where we would start, okay? Because we want to take the integral from 1 to infinity, so that's where we need to make sure that the function is decreasing, and it is. Excellent. So if, just a reminder of what the integral test says, if, let's see here, the integral from 1 to infinity of f of x dx converges, then the sum from 1 to infinity of f of n converges. So in this case here, this is our function. So determining if this series converges is the same as finding out if this integral converges. If the integral converges, we may conclude the series converges. If the integral diverges, we may conclude the series diverges. All right. So the integral from 1 to infinity of x over x to the fourth plus 1 dx looks like something that you might have to use trigonometric substitution on. However, it actually works out that this is just a multiple of arctangent. Okay, so the integral here is going to be equal to the limit as b goes to infinity of the integral of x over x to the fourth plus 1 dx. But in order to use arctangent, right, this is x squared being squared, and the derivative of x squared is 2x. So I need a 2 here and a 1/2 here, and that allows me to recognize that this is arctangent. So this is equal to the limit as b goes to infinity of, I can throw the 1/2 out front of this yet, that's absolutely fine. Arctangent x from, I forgot to put the integration bounds on here, 1 to b, so 1 to b. So this is the limit as b goes to infinity of, got the 1/2 out in front still, plug in b, this is the arctangent of, oh, and that should be x squared, so arctangent of b squared minus the arctangent of 1. Of course, tangent is equal to 1 at pi over 2, so this is just, pi over 4, so this is just pi over 4, and as b goes to infinity, then arctangent would approach pi over 2. So this is just pi over 2 minus pi over 4, and of course we're looking at 1/2 of that still, so this is pi over 8. Thus, this integral converges And since the integral converges, our series converges. So hence, the integral from 1 to infinity of x over x squared, sorry, x to the fourth plus 1 dx converges. And the sum from n equals 1 to infinity of n over n to the fourth plus 1 converges by the integral test. Excellent. So one more time, the integral test says that the integral of this function from integration bound to summation bound to summation bound, right? Integral from 1 to infinity of this in terms of x converges and diverges just as the sum does, or just as the series does. So when the integral converges, the series converges. When the series converges, the integral converges. Same can be said about when it diverges. When one diverges, the other diverges. So in this case, the integral converged, so we conclude that the series converges as well. And that's how we handle the integral test. All right, I'll see you guys again a little bit later for some examples on p-series. So we'll see you guys again soon here in the workshop.